Hello everyone, welcome to Electronics Prepper, the channel where we try to learn as much as possible about electronics to become more self-reliant with technology and prepare for the future. Somewhere at the beginning of the month October, I showed you a video with two different circuits that can potentially replace a Zener diode. Those circuits were relatively simple. One had a bipolar transistor, the other one had two bipolar transistors, and I've discussed then the differences in performance and all sorts of other details. Well, today I want to show you a third option that we have whenever we need something like a Zener diode to give us a relatively stable voltage that does not fluctuate with the change in input voltage. And this is a much better circuit than the previous two ones. Of course, it's also a more complex circuit that involves 5 bipolar transistors and several resistors. But of course, if we want better quality, it may only make sense that we need to have more components that do more thing in our circuit. So this is a circuit that I've simulated in microcap, and earlier I've actually tested on a breadboard, so I made sure that it performs well before I make a video and show it to you. And I'm gonna explain how this works. Before that, bear in mind that we might have two situations when we might want to use something like this, okay? Or perhaps three situations. The first situation is when we need to have a certain voltage for which we do not have any Zener diode commercially available, okay? With such a circuit, we can just adjust the output voltage as we like it, okay? So this brings us a great deal of flexibility. The second reason why we might want to use such a circuit is because a Zener diode, a typical Zener diode, requires a minimum of 5 milliamps of current passing through it in order to work correctly. If we give her less current, she will give us less voltage, and the voltage is not going to be so stable, and well, yeah, overall it's going to be a problem. So with a typical Zener diode we need 5 milliamps of current. There are some Zener diodes that require only 2.5 milliamps. There are special integrated circuits like Tele 431, which require only 1 milliamp in order to work, and they can work from 1 to 100 milliamps. But still, sometimes we might find that we need something like this that can work in the hundreds of microamps range. Like when we are trying to use something like this in a battery operated circuit and we want to draw as little current as possible, well then we are forced to come up with a solution that, you know, uses less current, and therefore we cannot use a Zener diode. And in some cases we might not be able to use a special integrated circuit either. The third situation in which we might want to use such a circuit is when we want to have something like this for relatively high voltages, okay? Because TL431, if I remember correctly, works with a maximum of 40 volts. I'm not 100% sure, it might be 30 something, it might be 40, but anyway, we cannot get too high okay? But maybe we need a stable voltage, like a stabilized voltage, in the order of multiple tens of volts, maybe hundreds of volts. Well, we could easily create such a circuit that would replace that particular Zener diode, because we can find, without big of a problem, bipolar transistors that actually withstand 200 volts, 300 volts, 400 volts, maybe even more, okay? So we could easily have the equivalent of a Zener voltage of 100 volts or of 200 volts of whatever we want, okay? So those are three cases in which we might actually want to use such a circuit. Now, how does it work? Well, it's not difficult. It's relatively simple, and it's based on the fact that we have these three transistors connected in such a way that they need to reach a certain equilibrium, okay? And T4 and T5, if you take a look at them, they form the so-called latching circuit. This is a latching circuit. Whenever one of these transistors start to open a little bit, it will automatically open the other one a little bit more, which in turn will open the first one more, and so on. And it's gonna happen really, really fast, that both of them will open to the maximum, will get into saturation, and they will remain like that, okay? So in English you call this a latching circuit, because it, once one transistor opens, the whole circuit latches, okay? Now this is nice, but we want this circuit to latch in a very specific way, in which across it we have a constant voltage. So in order to do that, we need to make it unlatch as quickly as it latches, and we need to make it sort of get into a state in which it latches only if a certain voltage is reached, and not before that, okay? So for that, we need to make sure that only one transistor out of these two, T4 and T5, only one transistor gets to be the one that controls the latching process. And for that, we need to use T5, and therefore we need to make sure that T4 remains closed whenever T5 is closed. So for that, we put a resistor, a relatively small resistor, between the base and the emitter of T4. I chose a 100 ohm value. It can be slightly bigger, but not a lot bigger, because then the whole circuit will tend to latch a lot sooner and remain latched, which we do not want, okay? And at the same time, whenever the circuit latches, what it happens is that basically both emitters come very, very close relative to each other. So across it, the voltage drops quite a lot, but it doesn't drop enough to make this whole circuit unlatch all by itself. So in order for it to unlatch, we need to have a third transistor, which is T3. It is connected in parallel with T5, at least the base and the emitter, so that when T5 opens, the T3 transistor also opens, but its collector is connected to the whole latching circuit, so that when this circuit latches, T3 will also pull down everything, which will basically reduce the entire voltage more than the usual, okay? The latching circuit will no longer have enough voltage for their base emitter junctions in order to remain latched, so it will basically unlatch. automatically. Okay, and this process only happens because we have these two resistors, Ru adjust and Ru2. This whole process will only happen when there is enough base emitter voltage on T3 and T5. But this voltage is a fraction of the entire voltage of the whole circuit, of the whole latching circuit, okay? So because of that, we get to have across the entire circuit a certain relatively stable voltage, okay? Once this voltage is reached, once the voltage tends to increase a little bit, T3 and T5 open, the T4 and T5 latching circuit latches, T3 will immediately drop down the whole latch so that T4 will stop conducting. Okay, the voltage will drop a little bit. Because it will drop, T3 and T5 will no longer have enough voltage to remain open, so they will close. The voltage will then start to increase a little bit, and the whole process will essentially restart from scratch. But this happens so fast that overall the effect is that the entire circuit will enter, I guess we could call it a steady state, a state of equilibrium, in which the voltage across it will be that particular voltage that we want to have, okay, which is dictated by the ratio between the adjustment resistor and R2. And although it's not possible for us to have a very precise mathematical formula for the output voltage, we can have an approximate formula because, like I said, the total voltage, which is the output voltage, by the way, I forgot to convert into English. I will do so right now. So the total output voltage is directly proportional to the voltage at which the whole latching circuit works. So we can have a rough formula that looks like this. The output voltage, okay, it's U indice Z from Zener. It's approximately equal to the sum of these two resistors divided by the resistor between the base and the emitter, multiplied by the voltage required to open this base emitter junction of these two transistors, which is typically 0.7, 0.6 volts. Okay, so this is roughly how to calculate these values. Now, one last thing that we need to mention is that unlike a normal Zener diode or TL431 or any other circuit that is similar to those, unlike those, in those cases when we can just use a resistor in series with our Zener diode in order to provide the necessary current, here we cannot simply use a resistor because the variation of the input voltage would cause a too big variation in current, which in turn will cause a too big variation on the output voltage. So this whole Zener replacement needs to be powered from a constant current circuit, okay? And for that we have T1 and T2. They are connected this way. We have R3 polarizing resistor, which can be of a relatively high value, in my case 560 kilo ohm. especially for the cases when the constant current that we want is relatively small, like in the order of milliamps or smaller. And this reset resistor is the one that basically dictates the current that this circuit will provide. The idea is that normally T2 is conducting because it's opened by this R3 resistor. However, the current that passes through it also passes through this reset, which is placed in parallel with the base emitter junction of transistor 1. The collector of transistor 1 is connected to the base of transistor 2, so basically when the current through transistor 2 becomes too big, the voltage across reset becomes big enough to open transistor 1, which in turn will close transistor 2. Okay, so when reset is about 0.6, 0.7 volts, transistor 1 will open, and this voltage appears on reset when the current is high enough. So basically the constant current that we have is essentially about 0.7 volts divided by the value of this resistor, reset. Okay, and this is how you calculate based on what current you want to have. So I will not show you exactly how this works on a breadboard, because it would be boring. It would be just a set of measurements that would need to be taken and written on a piece of paper. I've done that already, so I will just show you the results. I've made two different sets of tests, one with the current of 230 microamperes and one with a starting current of 500 microamperes. So what I did essentially is I adjusted readjust so that it has pretty much zero ohms, okay, so that on the output we have the minimum possible value. I have set the source voltage to initially to 3 volts, and then I have set the reset resistor, which in my tests were it was an adjustable resistor, okay, so that I can have 230 microamperes of current. And then I used readjust to set the output voltage to 2 volts, okay. So we start from 3 volts and we set the output voltage on 2 volts. We leave everything in place and we just increase the input voltage, so the voltage on the source, okay. And we measure the current through the entire circuit and the output voltage to see how they fluctuate. The output voltage, I went from 3 volts input voltage all the way to 28 volts. The current increased from 230 microamperes to 308 microamperes, and the output voltage increased from 2 volts to about 2.33 volts. Okay, so we can see that we have a significant output voltage fluctuation, but not so big. It's acceptable considering we have increased the input voltage by 25 volts. The output voltage has increased by only 300 millivolts for 2 volts. That's like 15% an increase, something like that. So it's not bad. Then I made the tests again, but this time by setting the output voltage to 4 volts and of course starting the input voltage at 5 volts. This whole circuit requires to have at least one more volt on the input than on the output. So the voltage drop across this constant current source is about 1 volt, give or take. Okay, so when I did this test with 4 volts on the output, I got only a 10% increase in voltage across a 23 volt difference in input voltage, which is slightly better than while having a lower output voltage. And then I increased the output voltage to 9 volts, and I started with the input voltage at 10 volts, and I had half a volt increase, which is about 5% or so, for input voltage going from 10 to 28 volts. Okay, so these results are not bad, but then I increased the current through the whole circuit to 500 microamps, and I essentially I run the tests again, this time only with 2 volts output voltage and 9 volts. I skipped over the 4 volt one, but it doesn't matter because at 500 microamperes starting current, going from 3 to 28 volts input voltage, the output voltage has almost not increased at all, both when the output is 2 volts and also when the output is 9 volts. Even though, just like in the first case, the current did increase from 500 microamps to 629 microamps, but the output voltage stayed a lot more stable. So from these tests we draw 2 conclusions. 1, the circuit works and works pretty well. 2, we have more stability of the circuit and basically a smaller variation in output voltage the higher we have the current going through the entire circuit. Okay, and vice versa, the lower we set the current, the more the output voltage will fluctuate. So that's about it. It's not rocket science, but it's definitely a useful piece of circuit that it's nice to have. It's nice to know that it exists and it can be used whenever we need to. So thanks a lot for watching my video. If you liked it, please hit the like button and perhaps even subscribe. If you want to support my work, there is a Patreon channel. Feel free to help me financially, because the faster I can buy components and electronic devices, you know, lab devices, the faster I can learn and the faster I can come here on YouTube and show you through my videos how to do various things, so that you don't have to do the same work that I do, so that your life becomes a bit easier. Thanks a lot for watching, and I will see you soon in the next video. Bye bye.